Also, one point to remember, it does not operate with respect to birth cycles, but operates with respect to T state. Okay? What is T state? What is birth cycle? We will come to it shortly. If you have done 885, that means you know this already. Okay. So, execution unit, as I have told you, has following parts: arithmetic logic unit, flag register, general purpose register. We have control unit, decoder also, and a pointer and index register. Okay. So first, ALU. So as you already know, ALU it performs as an 8-bit or 16-bit. So that is the advantage of 8836, that it can perform 16-bit arithmetic and logical operation. That means AND, OR, increment, decrement, complement, so on and so forth. Okay. So it has got 16-bit operand register which holds the operand which is not available to the programmer. Okay. So this is part which we have covered. Now we move on to our flag register. Okay. Flag register over here is 16-bit. So if you remember, in 8085 it was of 8 bits. So what is the flag? Yes?
Yeah, can you please connect your earphone again, because your voice is not clear.
It is not clear.
So like I'm able to hear, but it is a little dull. So I
Yes,
don't know.
ma'am.
Okay.
Yes.
Just give me a second. I'll just change it. Okay. Better now?
No, ma'am, not clear.
Hello.
Yes, ma'am.
Yeah, it's audible now.
Yes, ma'am.
Yeah, sorry, I couldn't hear you. I could see that you were talking, but it was not audible to me. Fine. So this part I don't have to repeat again, na? That's fine, right?
Yes, ma'am. Fine.
Okay. Yeah. So now we move on to our flag register. Now flag register over here is 16-bit, right? In that 9 bits are 9 are active flag. So it is not bit, it's basically each and every bit corresponds to certain flag. Okay. So purposely they are given in the different color so that you will understand. Okay. Nothing to do with the color. Okay. So we have 3 control flag which are DF, IF and TF, and 6 are status flags. Okay. Now as the word suggests, status flags will tell us the status of the operation. What kind of operation, whatever operation ALU has performed. So because of that, these flags will get set, okay, based on the result. Okay. And that is why it is a status flag. And if we want to control, as a programmer, want to control certain action, then these 3 flags we can utilize. And that is why the word is control. Okay. So we'll start with one by one. So first one is the carry flag. As the word suggests, the carry flag will be set. See, by default, all these flags are usually, or flag register is all zeros. Okay. So when you boot the system, everything is 0, right? And then when, because of the addition or subtraction, if there is a carry or a borrow in subtraction respectively, if it occurs because of this arithmetic operation, then only the carry flag will be set. So this bit will be set. Okay. This flag is also used in some shift and rotate instructions. So when we do instruction set, at that time we will again come back to. Next one is the parity flag. As the word suggests, parity, that means if the result of the operation has got even number of ones, then this bit will be set. Okay. So that is about the parity flag. Next one is the auxiliary carry flag. That is AF. Okay. Auxiliary carry flag. So the flag is set if there is a carry out of the lower nibble to a higher nibble. Okay, what is a nibble? What is a nibble? 4 bits. Okay, lower 4 bit or 4 bits is a nibble. Okay, so if I am doing 8-bit operation, lower 4 bits से higher 4 bit को, if there is a carry which is moving, then it is called as auxiliary carry. It is, so there is a difference between this carry and auxiliary carry. This carry is set when there is a carry out of MSB. So most significant bit se bhi bahar ek carry hai, that times this is set, and auxiliary carry is from lower nibble to higher nibble. If the carry is there, if I am getting a carry out of lower nibble to a higher nibble, in case of 8-bit operation, then it will be auxiliary carry. So on and so forth for lower order byte to higher order byte in case of 16-bit arithmetics. Okay, it is also used for all BCD operations. Next comes the zero flag here. So zero flag will be set if the result of my operation is 0. It is very simple. It is quite straightforward. All these flags are. Now, the most important ones are sign flag and offset flag. Now, sign flag will be set if the arithmetic or logical operation, the MSB of the result is 1. Just remember this, it copies the MSB. Okay, so if the MSB of the result is 1, right, in my arithmetic and logic operation, sign flag will be set. Okay, ideally, we need to use this sign flag to indicate whether the result is negative or not. Okay, so and so if you remember, we have something called as integers. So we have positive numbers as well as negative numbers, right? So if the result is negative, how you are going to depict that? Okay, for that I have to use the sign flag as well as overflow flag together. So remember this part. Okay, so here what we are doing is the sign flag is set if the arithmetic or logical operation resulting in MSB which has MSB of 1. So it just copies the MSB. Remember that. Okay, and the overflow flag is used to detect the magnitude of the overflow in signed arithmetic. Okay, what is signed arithmetic? Can anyone tell me? What are the signed numbers? So if I'm doing 8-bit operation, let's say, okay, if I'm doing 8-bit operation, right? So for unsigned number, I'll be using all 8 bits. So I will have 2 raised to 8 means 256 combinations, or 256 is the maximum number which I can 256 total numbers which I can depict using these 8 bits. So I have 0 to 255 is my range, correct? Because we are starting from 0, so it goes up to 255, and this is for unsigned integers. So now if I have signed numbers, my MSB will be utilized. Okay, as so if I want to depict any 8-bit number, I will have, let's say, 00 I am representing. Okay, just for simplicity. Okay, so I have this 8-bit, this 8-bit. So this is 0. Suppose I want to represent positive 1, this bit will be 1. Correct? Okay, so totally these are 7-bit, this is the 8th bit. Correct? So now when I am going to utilize the unsigned, or it's a negative number. Correct? So this is what you have done in your earlier subject. So now I have actually how many bits remaining? 7 bits to remaining to represent the number. So 2 raised to 7 is how much? Can somebody tell me quickly?
120.
It should. Very good. So it is 120. So I will have 0 to 127 as my positive number and minus 128 till minus 128 as my negative number. Okay. So now if my result is beyond this limit, okay, overflow flag will be set. Okay. So if my result is beyond these limits, if I'm doing 8-bit operation, my overflow flag will be set. Okay, so we are not going to just check sign flag, but we are going to check the overflow flag also. Okay, just wait for some time. I'm going to give the example also, and then we can confirm it. Okay, or should we directly, let me directly go to the example. Okay, so here, if you see, try to do it on your own. So it is 7f plus 1. All right. So this is a positive number. We are doing addition. So ideally, I want this answer to be positive. Okay. Ideally, I want this answer to be positive. I know I'm working with positive number. I'm doing the addition. So 7f means 0, 1, 1, 1. F is 1, 1, 1, 1 plus 1, 0, 1. Right. It is in hexadecimal. So it is, sorry, 0, 0, 0, 0, 1. Okay. So if I add this, what I'm going to get? 1, 0, 0, 0, 0, 0, 0, 0. So 1 plus 1, 0. This one, 1 plus 1, 0. So there is a auxiliary carry now generated from lower nipple to higher nipple. Okay. So just see what all various flags. Is there any carry generated out of MSB? No. So my carry flag would be 0. Okay. How many numbers of ones are there? Odd. So my parity flag will be 0. Correct? Then there is a carry from lower nipple to higher nipple, isn't it? Okay, I hope you can do this little bit of arithmetic. Okay, hence my auxiliary flag is 1. I'm doing 8-bit addition. Please remember that. So is my answer 0? No. So my 0 flag is 0. Okay. What about sign? SF sign flag? It will be 1 because it just copies the MSB of the result. Isn't it? Okay. Since my 8 bit, that is 0 to 7, means 7th bit is 1, my MSB is 1. The sign flag is 1. Okay. Also, my overflow flag is 1. Why? Because now I have gone beyond the limit of 127 and hence the overflow flag is also 1. Okay. Understood this? So this is about the status registers. Shall we move ahead with the control registers? Please confirm.
Can you explain that overflow flag?
Okay. Now overflow occurs means what? What is overflow means to you? If the number is beyond these limits. Okay. See, I have to decide right now whether I am working with signed numbers or unsigned numbers. Right? So being a programmer, I should know that logically if I'm doing 8-bit or if I'm working with 8-bit, okay, my MSB will be secured or it is kept aside to bifurcate between unsigned integers and signed integers, isn't it? Correct? So 7f plus 1 will give me 80. This is nothing wrong because 80 is a positive number. Correct? But 80 has gone beyond. So 80 is 128. Na? So in unsigned integer, this is beyond 127. Correct? And hence overflow flag is set. Understood? Yes. So we should not interpret only from sign flag, but we have to take care of overflow flag also. This is what is meant by this. Otherwise, what you will feel 101 means 80 means 1 triple zero, 4 times 0. If that is the answer, and if I just check sign flag, I will interpret that the number is negative, right? But that is not the case. Understood? Now? Okay, so I should not consider only sign flag. I have to see the overflow flag. So as we move ahead with the programming, this will come again. Clear? Who has asked this question?
Yes.
Siddhant, understood, right? Okay. Perfect. Then next is trap flag. As the word suggests, it is one way to run the program, okay, instruction by instruction, okay, or if you want to like see the contents of the use registers, memory variables after every instruction, okay, then this trap flag is set to 1. So by default it is 0. Okay, so the single stepping is not done. So if you have done C programming, आपका F7 F8 अगर आपको याद है, right, you can debug your program using that if you have ever used it, right? Okay, in your first year. I hope I am still audible, right? So yeah, so when I set my trap flag to be 1, now this is a control register, right, or control flag, right? In my flag register, this is the controlled flag, right? So if I set it to 1 as a programmer, then I know that I'm going to do single stepping because I would like to see the content of the registers which are used in the program and memory available. So if my logic is going haywire and if I want to check how these registers contains memory contents are changing, I should do single stepping. Okay. Okay, so the trap flag is used for single stepping through a program. Next one is the interrupt flag, IF. It is used to allow or prohibit the interruption of a program. So usually it is 0. So when any of your system is booting, right, there is always an idle time, if you remember. Right? Even if you press the keys, nothing happens. Why? Because we cannot interrupt the system in between. So आपका mobile भी put up हो रहा है, so it always asks you to wait, na? Right? Okay. So this has to be set. Okay, if a certain type of interrupts, that is maskable interrupts, can be recognized by 8086. Otherwise, the interrupts are ignored. Okay, what are maskable? Something which I can mask, I can hide in a way, right? So that is what we call as a maskable. Anyway, those who have learned 8085, they know what are interrupts, what are maskable interrupts. Those who do not know, wait, we will come to it. So right now, just remember, if I do not set this bit, certain type of interrupt cannot be recognized by 8086 or 88. Though I could give that interrupt, or if the system is also interrupted or processor is interrupted or that interrupt is generated, the processor will not get interrupted by that. Okay, that means my 8086 will not recognize that as an interrupt. So those interrupts are ignored. Next one is the direction flag, that is DF. This is used with string instruction. So if DF is 0, the string is processed from the beginning. See, usually if we want to do block transfer, okay, this is again one of the favorite program here, right? So usually, as I have told you, all bits are 0 na, at the beginning, right? Status bits will get changed depending upon the result. So if I don't change these bits, okay, by default they are 0. So here, if DF is 0, the string is processed from the beginning. So our usual way is what? We start from the beginning. Nobody starts from the bottom in a way, right? Okay. So from first element to the next element. So even if you are processing an array, let's say somewhere in other programming language, still you were doing it from the lowest to highest, isn't it? That is usual way of doing it, right? But if I want to do it in the opposite manner, then I have to set this direction flag as 1. Okay, if it is 1, then the string is processed from higher address to the lower address. It is not content of the memory, right? It is the address of the memory. So block transfer if I am doing, so if these are the data from a particular memory location, I have to move to some other location, right? So if DF is 0, it will start from here and it will go to first place here, let's say. But if my DF is 1, it will start from the, what you can say, the element having the highest address, right? Okay, or maybe from whatever you call it as, okay, depending upon your end. So not from the first element, but from the last element. Is that clear? Perfect. So there is no doubt now with the flag register. Is this part clear to everyone?
What difference will that make?
हाँ, अगर आप स्टार्टिंग से सपोज आपको 10 नंबर्स दिए हैं 1 to 10 and if I ask you to copy them, let's say, okay, so you are starting with number 1, you are starting, let's say यहाँ पे हर एक मेमोरी लोकेशन में एक नंबर है, right? Let's say अभी 5 ही लिख रही हूँ मैं. So if DF is 0, it will first copy 1, then 2, then 3, then 4, then 5, right? But if DF is 1, what will happen? It will start with this number or this memory location. Got my point? And then go opposite. Then it will get decremented. Our IP will get decremented. Okay?
Yes, ma'am. Got it.
Got it? Huh? I should not say instruction pointer, but it will get decremented. Okay, this could be stack, this could be anything else, right? So it will get decremented. So instead of copying 1, 2, 3, 4, 5, I'm doing 5, 4, 3, 2, 1. Clear? So I have changed the direction. Perfect? Okay.
Yes.
Yeah. Apart from this, now the flag resistance is over. Okay, flag register is over. Then you have ALU we have done already. Okay. Then we have this general purpose registers. Now these registers are individually, they can work as 8-bit register as H, AL, BH, BL, CH, CL and DHDL. Okay. So lower byte is always stored in AL and higher byte is always stored in AH or in L type and in H type in respective registers. Okay. So together I have this 16-bit registers as AX, BX, CX and TX. So individually AL, AH, BL, BH, CL, CH, DL, DH. Remember this way so that you will always say that the lower byte is always stored in L type. Okay, whether this whatever is that, whether it is A, B, C or D. Okay, and if I ever have to use 32-bit register, it is always a combination of DX and AX. So DX will have higher 16-bit and AX will have lower 16 bits. Okay, understood?
Yes, ma'am.
Yes, ma'am.
16-bit A higher 8 bits. Then if I have to use 32-bit register, it's lower 16 bits and DX will have higher 16. So whenever X is there, that means it is 16-bit. Okay, otherwise we call it as L or H, low or high, in a way that way you can remember. Okay. So these general purpose registers also have certain special functions. Okay, though I can use them as general purpose register, there is a specific work associated with each type of that. Okay, so AX register together forms a 16-bit accumulator. So it holds the operands and results. So it holds the data during IO operation, also during string operation, right? But if I have to use 8-bit accumulator, which register I should use? Yes, AX is 16-bit, right? So if I want to use 8-bit accumulator,
But we could use AH or AL for that.
no,
Higher
we
or low.
use AL. Okay, we go for AL. It's not AH. AH higher है ना?
Yes, ma'am.
Okay. AH will be utilized automatically later on. That we will understand when we move ahead with our instructions. But basic lower byte would be stored always in AL. That way you remember. Okay. So it is A. Clear?
Yes, ma'am.
Yeah. Then we have BX. So BX is the only general purpose register that what is indirect addressing, which holds the memory address in base relative addressing mode. Okay, I will explain you that again when we are doing it. So if you see it right now, sorry. Huh? So just understand this instruction. Move square bracket bx comma ax. So always the destination is mentioned and then the source, right? So this particular instruction is moving the content of ax into the memory location, which is whose address is given in bx. Okay, whose address is given in bx. Okay, remember that. So it is the only general purpose register which is used for indirect addressing. Okay, which is used for indirect addressing. Okay, also it is called as a base register. So as you we move ahead, you will understand why it is called as a base register again. Okay, so that is why BX is the AX stands for accumulator, BX stands for base register. Okay, next comes the CX, which is again a 16-bit counter register. So it is a default counter register for 3 instructions like loop, rotate, and with the string instruction. Okay, so if I want to use this loop, rotate, so it holds the count for that. In loop instruction to indicate the iterations, and in shift rotate instruction it is used to indicate number of shifts or rotations. Okay, if 8 bits are required, only CL is used. Okay, so that rule is common. Just a minute. Yeah. Got it now? Accumulator, 16-bit accumulator, BX my base register. Okay, this pointer register you can say, or the base register you can say, in case of indirect addressing mode. Right now, just remember. So it stores the base address. CX is my default register. Okay.
Hello, ma'am. Actually, your voice is breaking.
To protect. Sorry. Hello. Is it audible now?
Voice is like.
Let me see. Yeah, is it proper now? Hello, can you hear me now? It's not lagging right now.
Not lagging.
Or is it still not lagging? Okay, good. So I just changed my network. I hope it will work now. So CX register is used for all these type of instruction. Also in string instruction, which has got a prefix of repetition to indicate the size of the string block. Next comes the DX, which is a 16-bit data register. It is used with AX to hold the result greater than 16-bit. This is what we have seen earlier also. It used to hold either the port number for in and out instruction, and also used as a pointer for 16-bit address access of IO port in indirect addressing mode. Okay. So just remember, there is something called as indirect addressing mode. So indirectly, I'm going to address the memory or give the address of the memory location. So that will be my indirect addressing mode. Okay. Next comes, so those were general purpose registers. Okay. Next comes our control circuitry, which is used for directing the internal operation. So instruction register and instruction decoder, which are not shown, but obviously they are there. They fetches opcode from the queue into the instruction register, and the instruction decoder decodes it and sends the information to control unit for execution. Okay, so that is all is present over here. Right? So we have done this part, we have done this part, we have done this part. Now the last part which is remaining is is our base, the pointers and index registers. Okay, and I hope you know this. Decoding is a process of translation from instruction to action. Okay, so here comes our pointer and index registers. So they are used to hold 16-bit offset of a data word in one of the segments. Okay, so stack pointer, SP stands for stack pointer. Then VP stands for base pointer. SI stands for source index and DI stands for destination index. All of them are of 16-bit. Okay, so now every time when you see 16-bit, when you think about memory, you all have to remember वहां से 16 bit से my BIU has to generate 20 bits address. Okay, always remember that 20 bits physical address is required for to go to a particular memory location. Okay, so 16 bit में हम लोग सिर्फ offset देते हैं उसका या a location देते हैं in that particular memory segment. That's all. Okay. So the first one is my base pointer, which is again 16-bit, which holds 16 bits offset related to the stack segment register. Okay, so it is specifically used when we want to pass a parameter via stack. Okay, so it is also used as an offset register in base addressing mode. Okay, so BP is base pointer is basically stack and base pointer. These are basically used in random access of the stack. So by default, when I'm giving base pointer, it is the offset for stack segment. This is what you have to remember right now. Okay, so if base pointer, if you see, it will always go to stack segment. Okay, and I can use or I can use the stack in the random access, or I can randomly access the stack. Okay. Next one is stack pointer. As the word suggests, obviously it is will be relative to, so it will hold 16-bit address, offset address relative to stack segment. Okay, so offset you all remember now. Okay, अगर ये मेरा stack segment है, तो stack segment register will have the base address, right? And then 16 bits uska offset will be present now in SP. Okay, wherever I want to point to, and always SP points to the top of the stack. Okay, SP always points to the top of the stack. Clear? Okay, and it is used for sequential access of the stack, not random access of the stack. Okay, so suppose the stack is now over here, right? So SP will point here. Clear? And then it will get incremented. So now my memory locations are moving up. This is the lowest one. This will be the highest one. Okay, and yes,
technically it should a stack generally when we actually push an element onto a stack, so it like the top point increments by one or the number of or the size of each element. So ma'am, if you already put it onto the top, so like in that case, like ma'am, it's already
good
at the maximum.
So you are listening.
Yes, ma'am.
Okay, good. Yes, yeah. So what is stack basically?
Ma'am, and stack is a data structure where we can only perform insertion and deletion from one end.
Okay. So when you insert it, you increment the stack pointer or you decrement the stack pointer?
Ma'am, we increment it.
Incrementing. So you go to
Ma'am, like we start from in our implementation, we start from -1,
okay.
and then if the top pointer points at -1, so the stack is basically empty. So, ma'am, over here we could compare it
Very
with
good.
SS.
So I'm also saying the same thing, isn't it?
Yes, ma'am. Like, but ma'am, if it's already on the top, then if we try to
I
increment
didn't
it,
say it is on the top. I said the base is over here. Base segment. Sorry, the stack segment. The what you can say the base memory location. The starting memory location is this.
yes, ma'am. So, ma'am, like,
So that is there in stack segment, which is there in BIU.
yes, ma'am. So, like, if the stack pointer already points to the top of the stack, as in the
हाँ देखो आपने 5 numbers push किए तो where is your stack pointer?
oh, oh, अच्छा, okay, ma'am. वैसे
हाँ, it is always said in that way ना. Usually it is -1. So I am not saying it is by default somewhere. I am saying offset है ना. ये offset का wording बता रही हूँ मैं आपको. Okay? It could be at this position also. I am not saying it is not at this position or somewhere else. Correct? I did not start with that. I am making you understand what is offset. Okay, so
got it, ma'am.
according to your logic, let's say you have pushed 5 numbers. So now your stack pointer will be at the 5th position, according to you, right? Position, huh?
Yes, ma'am.
Right? And when or 6th position?
Ma'am, the index would be 4 and the position would be 5.
Correct?
Yes, ma'am.
Perfect. Okay, so is it right? Okay, and then again the whenever the next word or next number comes, it loads that and then again it gets incremented. So I'm also saying the same thing. So I have not spoken about this. This is stack segment ka beginning point part hai. Okay, at which memory location? Suppose it is 0, 1. Any number, let's say 1000 pakad lo H mein. Okay, it is very easy to say. So this will be there in my stack segment. Okay, which is a part of my BIU. Okay, हमने इसलिए पहले BIU लिया है. बस इंटरफेस यूनिट में, do you remember मोहित? Right? We have a stack segment there, right? तो मैं वहां का रेफर कर रही थी. Okay, so this will be there in this, and the stack pointer will always have the offset address. Okay?
Yes, ma'am. Got it, ma'am.
नहीं, मुझे confusion क्या था वो ही नहीं समझा. So sorry.
No, ma'am. Like, ma'am, basically, ma'am, मुझे लगा कि top of the stack as in top of the जो segment था उसके top पे. नहीं.
Segment के top में नहीं. वही तो logic है ना यहाँ पे मोहित. यहाँ पे stack segment का जो starting position है, it is stored somewhere else. Okay? My stack pointer is not always locating to the starting position of the stack memory, isn't it?
Yes, ma'am.
Got my point? That will hold the current position of the stack.
Yes, ma'am.
Sequential access है ना. जब वो empty हो जाएगा तो it will come down. When it is still full, it is going up. Correct?
Yes, ma'am. So it will keep incrementing until we reach the top of the total allocation.
Yes.
Yes, ma'am. Got it, ma'am. Thank you, ma'am.
Okay. Anyway, we are going to see this again and again. अभी बहुत instructions और इसके साथ वापस से we have to see it. It's good that you have pointed it out. Fine. Okay. So next one is the source index. That is SI, which is again 16-bit. So it holds the 16-bit offset of a data word in the data segment. Okay. So SI, DI, again they are related to data segment. Data segment ka the base location is where? It is in data segment in BIU. Always remember. Okay. So if the source index has got 16-bit addresses to F32, right? And the data segment register, this is now in BIU, okay, has got 2000. जैसे अभी मैंने 1000 का example दिया. So what we have studied in last lecture, 2000 into 10H, okay, plus now this SI register. So this is how 20-bit physical address will be determined which is a location in my data segment. Okay, and that is why they are called as offset or pointer index. Okay. Then destination index. So it holds the 16-bit address of the data word in extra segment, basically with the data segment and then the extra segment. Okay, so SI and DI are mostly used with the string related operation. Okay, so to move a block of a data from one memory to another. Okay, so there I'm going to use source index and destination index, and that is why the word index is there. So SP and BP were pointer, SI and DI were index register. Okay, so this is what you have to remember. With code segment, I always have pointer register is IP. Both of them are present in BIU, correct? DS, data segment के साथ I can use BX. With data segment, I can use SI, DI, okay? And DI is used with ES in case of string operation. With stack, I have stack pointer and base pointer. So stack pointer will move the thing sequentially, okay? Okay, it is for the sequential access of the stack, and base pointer is for the random access of the stack. Clear with this part? Okay, please remember these things, okay? And then as we move ahead, we are going to utilize it. Okay, so finally, if we want to differentiate between BIU and EU, BIU sends out the addresses and it tells where execution unit tells the BIU from where to fetch the instruction or a data. So BIU fetches the instruction from memory, execution unit decodes the fetch instruction. BIU reads the data from the memory and port where EU executes the decoded instruction. It is same. So BIU takes care of all the address and data transfer on the buses, and EU takes care of performing operations on the data. So it is also called as the BIU called as the external word interface of the processor, and EU is called as the execution heart of the processor. BIU works in synchronous with machine cycle, and execution unit works in synchronous with the T states. Okay. So here we complete the architecture. Right? Any question anyone has got?
Ma'am, can you show the previous slide?
This one?
इससे भी पहले वाला.
ये वाला?
Yes, ma'am.
Any doubt you have?
No, ma'am. 1 minute. Yes, ma'am. Done.
Okay, fine. So, is there any doubt about architecture?
No.
Okay, good. So now we move on because the next part is actually the same what we have done right now, but okay. Right. Now we are moving ahead with the next topic, that is addressing mode. But anyway, we are not going to complete all of that in whatever remaining time is, but at least we will start. To begin with this addressing mode, we should know what is the 8086 programmers model. So this is what we have just done it. So I just wanted to continue, right? So bus interface unit has got various register, extra segment, core segment, stack segment, data segment, and instruction pointer, correct? So if somebody asks you to draw programmer's model of 8086, you should be able to give all these things. Then EU registers or our general purpose register, AX, BX, CX, DX, right? Then you have pointers, stack pointer, base pointer, and index, source index register, destination index register, and flag. Okay, I'm not going to explain this once again, but this is called as a programmer's model. You should know it. Okay, so how these particular segments are being utilized. Okay, so the segment registers for, let's say, for code segment, stack segment, data segment, and extra segment. Okay, their offset has to be stored somewhere. So for code segment, it is the offset register is instruction pointer. For stack segment, it is stack pointer, base pointer. For data segment, it is source index and destination index. Okay, so this is what we have already seen, as well as sorry. Right, what is remaining now? The bx data register, which is used as a pointer to a data segment by default. Few things you can change later on by explicitly writing the code. Okay, but by default, what is there you should remember when we move ahead with the programming. Okay, so that what you can say, a silly mistake or stupid mistake, we should not do it. We have to remember these things. Okay, then this is about the programmer's model. This is what everything we have done. Okay, it is fresh in your mind. So now can we go ahead with the addressing mode? I will just tell you various types. Okay, first two we will do it and then I will stop, because the next memory addressing mode we have to do it at a stage, then only you will understand. Okay, or you can remember it. So what is the addressing mode? Address means I have to call you by name. Okay, then only you will pay attention, isn't it? It is something like either I have to call you by your number or your name, right? So the instruction may belong to one or more addressing mode depending upon the data types used in the instruction and the memory addressing modes which are there. Okay, so there are many types. So if you see different books, certain like few words are changed here and there, but that's okay. Okay, so the addressing modes describes the types of the operands and the way they are accessed for the executing an instruction, how they are presented in the instruction in a way. Okay, how my operands are given in the instruction. Based on that, I have different addressing modes. So all addressing modes also depends upon the type of the instruction. Okay, so according to the flow of the instruction execution, the instructions may be categorized as sequential control flow instruction and control transfer instruction. The words are pretty obvious. Sequential flow control means the instructions will get executed one after the other. So they transfers the control to the next instruction appearing immediately after it. And hence it is sequential programming. We all do sequential programming, right? Then comes our control transfer instruction. So where the instruction transfers the control to some predefined address specified in the instruction after its execution. So this is also we have done. If you have used some other higher level language also, we have done this control transfer instruction, but in the different format. Okay, यहाँ पे the mnemonics for that this would be different. Okay, so interrupt, call, return, jump. So these instructions they will change the or they will transfer the control of the instruction. So it is not moving sequential; it will go to somewhere else, right? Some other location. When we talk about addressing mode, so in general, what is addressing mode? How in the instruction I'm specifying my operands. Okay, so in basic way, I can tell you this: how my operands are now presented in the instruction. Okay, so it refers to the different methods of addressing or selecting the operands. Right? What is operand? What is operand?
Basically one of the basically something on which the operation is being performed on.
Correct. operation to be performed on, right? So I have to first give the operands and then only the operation would be performed. It is pretty logical, right? Okay, so how these operands are presented, that defines my addressing mode. So I have immediate addressing mode, register, memory, string, and IO addressing mode, and implied addressing mode. Okay, so so many are there, right? I'll just tell you the first one, that is immediate addressing mode. Then we will see the whole bifurcation once again. So in this type of addressing, data is immediately given in the instruction. So it is appear in the form of successive byte or bytes. Byte or bytes likha hai, that means it will be either 8-bit or 16-bit, correct? So when I write move AX, 0005H, what does this mean to you? Those who have not learned 8085 also should know this, isn't it? But I think your class has done it. That what I have told you, ये है opcode होता है इसका, right? वो बाद में आते हैं हम लोग इसमें, हाँ? This is my destination, this is my source, right? So what am I doing? AX is how many bit register?
16 bit.
16 bit. So am I giving 16 bits directly? Right?
Yes, ma'am.
Right. So what it is moving? It is moving 0005 in AX. So AL will contain what?
05.
05 and AH?
00.
Very good. Okay. So that is how the data is moved to the register. So why it is immediate? Because in the instruction itself I have given the data, right? That is why it is immediate addressing mode. So immediate data is moved into the register AX. Okay. So data can be 8-bit or 16-bit. So I could have written here move AL, 05H. Next instruction would be move AH, 00H. So it will also do the same thing. At the end of execution of those two instructions, I will be having 0005 in my AX, right? But my 8086 is 16-bit. It has got 16-bit data bus, right? So I can do 16-bit operations directly. So I can directly use AX, 0005. Correct? Clear?
Yes.
Yeah. And next one, quickly we will see here and then I'll stop. This is register addressing mode. So in register addressing mode, the data is stored in the register and it is referred using a particular register. Okay. So all the registers except IP can be used in this mode. Okay. So here what am I doing? Example of this is move BX, AX. So what does this mean?
Content of AX is copied in BX.
Correct. Content of AX is copied to BX. Okay. So here I'm using registers only as my source operand, as my destination operand, as well as my source operand, both. Okay. So they can be of 16-bit or they can be both are of 8-bit. Okay. एक 16-bit, एक 8-bit नहीं करना है ना. Okay. But it can be of 8-bit or 16-bit. Okay. So this will transfer the content of AX to BX. So that is register addressing. Okay. We'll stop here. Memory addressing mode, I need to do it together. Clear? Yeah. Somebody has raised the hand. Riya, any doubt?
Actually, we have a OOPS meeting now. Like Puna ma'am is meeting for the DSC students, so we have to leave.
Yeah. Anyway, I'm stopping now. Okay.
Thank you.
Just wait a minute. I'll take the attendance.
Okay, ma'am. Sure.
Okay. So understood today whatever we have done? No problem. So architecture we have finished. We started with addressing mode. Right? Somebody can confirm. Then I'll leave.
Yes, ma'am.
No issues, right, Riya? Okay.
Yes, ma'am.
Okay. Chalo, I'll end the meeting. Anyone has got any question or I will end the meeting?
No, ma'am.
Okay. Thank you. See you in the next week.
Bye, ma'am. Thank you, ma'am.
Yeah, bye.